Hello, everyone. Is this? Okay. So, as you can see, I'm not Chang Wang, which should have been here initially to present this. Sadly, he had an issue to get a visa, so that's why I'm doing the presentation instead of him. So myself, I'm the CTO, and I'm more like with an engineer background. So I will present you like some algorithm, and as I'm not the mastermind behind all that theory, please understand I might go a bit fast on some stuff. So if later you have some specific question about algorithm, I'll give you a way to contact Cheng also directly. Okay, so yeah, as Vitalik said, scalability is the single most important technical challenge that we have to solve if you want to reach mass adoption for blockchain. Basically, today, Ethereum and Bitcoin, they can achieve a maximum of 15 transactions per second, while if you look at a system like Visa, a worldwide system, it can go on thousands of transactions per second. So I guess you are more or less all well aware of that issue. We saw in the past, or still today, some solution to solve that. There is an on-chain solution that implies sharding. There is also a half-chain solution that we saw also today. And at Alephium, we believe that both are complementary and that in the long run, we should use them together. So clearly, Ethereum is leading the way for the research in that area. So it's a real pleasure for us to be here today. There's many progress being done. We could see that this morning in the keynote, so yeah, it's great. So many of the existing sharding algorithms that we see today, they are basically similar to Ethereum sharding. So in a nutshell, they rely on proof of stake and validator shuffling. I guess you got the idea this morning during the other presentation. And in some way, they all imply the usage of a two-phase commit when it comes to cross-shell transactions. So this is quite challenging in different ways. But first, like reshuffling introduced quite an overhead. Basically, to catch up the entire state of a new shard, that's expensive. Also, cross-shell transactions, well, actually, it's not so efficient because they have to be done in multiple steps. So yeah, it's not ideal. So at Alephium, we decided to take another approach, and that's what I will present you to you now. So we propose a new approach we call Blockflow. There's a white paper you can find on our website that describe in detail how it works. So it have an innovative consensus algorithm where we combined DAG, direct click acyclic graph, and sharding together. Thanks to that, we can support cross-shard transaction natively, which means you just do a cross-shard transaction in one step. It's just one operation. The network is vulnerable to 51 attack like Bitcoin and not 1% attack. And we also provide a practical solution for scaling smart contracts. So yeah, it's quite nice because all the main obstacles were resolved when we implemented the alpha version that we have currently working. We were able to run it on AWS, and we got some really nice metrics out of that. So basically, we're able to achieve a throughput which is higher than 10K transactions per second. So now I will give you a more detailed introduction about the algorithm and how that works. But before really getting into the detail of the algorithm, I just want to give you a quick sneak peek on the philosophy we follow. So basically, we believe that the evolution of the blockchain algorithm follows the same evolution path as the computation model. So you probably all were aware of this evolution of computing model. We started with sequential computing, and then we moved to concurrent computing, and eventually we reached distributed computing, which is basically a shared version of concurrent programming. So now if we think about a blockchain, how does that match, you know? Basically, sequential computing is the equivalent of the single chain, like the original Bitcoin paper. Then the equivalent of concurrent computing is the DAG algorithms. So we believe that the next natural evolution that corresponds to distributed computing is basically combining DAG with sharding. And that's what Blockflow is doing, and it's to our knowledge, it's the first of its kind to do this kind of combination. So let's see how the sharding works in practice. So our sharding approach is quite different from the existing ones. We use a scalable UTXO model, and we have 2 levels of sharding. So at the first level, we take the addresses and we share them into G groups. So G is a parameter of the network. Then at the second level, we take transactions and we share them into G times G groups based on their input and output addresses. So if you look on the left side, you see a little graph as an example. Here we have 3 groups, A, B, and C. So the transactions, they have 9 different categories, which correspond to any 2 of these 3 groups, right? So that's why we have 9 edges in this graph, and each edge have a unique blockchain, right? So now let's see what kind of property we get from this design, right? So first, well, let's say I want to do a transaction from one group to another. Let's say, for example, from group B to group A. Well, I can directly commit my transaction to this edge, to this chain, in just one single operation. So that's a pretty nice property. Also, if we look at what group B needs to download, right? Well, actually, he only needs to download what is highlighted in orange in this graph, which is basically all the transactions coming to this group and getting out of this group. And that's basically 2 times G minus 1 of the overall G times G shared. So that's also a pretty good property to have. So, of course, sharding is not just about sharding, right? It's also about reaching a consensus for all the shards. And that's quite complicated, as we could see right this morning in some of the talk. So in the network, each shard can have forks. So how do we ensure that eventually the network will select compatible and correct forks for different shards? That's basically known as a fork choice rule. And we had a great explanation about that this morning. So in Blockflow, we use a smart data structure to resolve the dependencies of the different forks. And we have one kind of DAG algorithm, which is then combined with a finality algorithm, and this way we reach a consensus. So to be a little bit more precise, in Blockflow, each block selects several block hashes as dependencies and pack them inside the block content, right? So each new block determine a unique fork for each shard, and that in a transitive way. That's very important. So in the end, our consensus algorithm is not that different from a traditional blockchain. The miners, in addition to packing the transaction, they pack the dependencies. And also the node, they have to validate the dependencies in addition to the transactions. So this is just a small example graph of dependencies between blocks, between each shard. So if we say that Aloïs, which is in group 1, want to send 10 coins to Bob, which is in group 0. So Aloïs first create the transaction and broadcast it to the network. The miners for C10 find some of the latest block in other shards. The miners pack those hashes and transaction into a block, and then the miners miner pronounce and broadcast it to the network. So the thing is that the hashes, they are selected based on a sophisticated algorithm. This is described in nice detail in the white paper. So with this algorithm, we don't have to include all the hashes of all the shards in the network, right? And at the same time, we can ensure that all the hashes are compatible with each other, so do some form of validation. So now let's do a quick analysis of Blockflow. So first, in terms of speed, you can find a more detailed semi-formal analysis in the white paper. But basically, we say that if the TPS of each single shard is P, then the overall TPS is P times G times G, right? So for a 10 megabit network bandwidth, we could choose P15 and G32, and you get over 10K transaction per second. Yeah, it's worth noting that even with a G of 6, you're already higher than 500 transactions per second. So in terms of security, as I said earlier, the system is vulnerable to 51% attack, like Bitcoin, but not 1% attack. And that's thanks to this block dependencies mechanism. Of course, all of this is nice, but it doesn't come for free, right? So what is the cost of using this approach? Basically, the main cost is that you need some spaces to store the block dependencies. If we take G equal 32, it's around 1 kilobyte with raw data, but there's a simple optimization that can be implemented, and we can get down to a couple 100 bytes to store that. Then there's also another cost in terms of validation that need to be done, but we believe it's quite negligible compared to all the overwork that has to be done at that time. So that's it for the theoretical part about the algorithm. And now I'll just, so now, yeah, let's see how the application of Alephium looks and what kind of advantages you can get as an D-app developer. So yeah, so our design philosophy is to scale what we believe to be the most useful functionality, and to rely on less scalable solution for the other functionality. So when I say the most useful functionality, we have in mind token actually. So the way we design that is we decompose the handling of smart contracts into a token protocol and a data protocol, and we support smart contracts into specific chains. So here, if you look on the graph, these chains here, A, B, and C, we call them the intra-group shared chain. And basically here we can keep a consistent state. So it's possible to run the smart contracts there. Oh yeah, and yeah, so with this, our token protocol is friendly both for users and developers because it's simpler to use than something based on a two-phase commit. So the user experience is roughly the same as if you were working within a single shard. So please also note that our token protocol is programmable to some extent, even though it's not Turing complete like a full-fledged smart contract language. So yeah, what can we do with that, right? What kind of thing we can do? So we all know that a lot of use cases will benefit from this, from having a scalable blockchain because of the performance improvement. So let's see a few examples where Alephium could actually have specific advantages over existing sharding approach, thanks to the algorithm we are using. First, we could actually build an efficient and fully unchained decentralized exchange that we still don't have today. We could also build prediction games that will run at large scale using the token protocol. And last but not least, for stablecoin, Bancor, or MakerDAO kind of protocol, the handling of the exchange could be done with smart contracts, while the token will be distributed among all the shards. So we think it's a really nice scaling property. But anyway, in general, thanks to this native cross-shard transaction support, roughly, I mean, all applications could achieve a better scalability. So thanks for your time, that's it. It was a pleasure to present Alephium to you. I hope you enjoy it. If you want to know more, please go to our website. You can access the white paper from here, and you have all the detail about it. In case you have some question, you can catch me around. For anything that is really related to the algorithm design, I will ask you to contact Cheng Wang directly. If you go to our website, we have a Telegram group, and you can join here. We'll be happy to help you. Yeah, thanks.